Hi there everyone, in this video we're going to be talking about confidence intervals. Now confidence intervals are really important things because what we're going to do is we're going to take a sample, and that's what the last video was about, taking a sample from a binomial distribution and we're going to produce a proportion. Because of the variability in our samples though, it's really important that we understand that that particular sample value we get is not necessarily the value for the entire population. We've talked about that, but what we're going to do today is we're going to create an interval that we can say with a certain degree of certainty that the population parameter, the population value, is going to be in that interval with a certain degree of certainty. So we're 95% confident that the population proportion is going to lie in this interval that we're going to construct. So I'm going to go through the maths behind how we get that interval and also just do a simple example of how that works. So we know from the central limit theorem about the sampling distribution of the proportion. We know that when we take samples from a population, as long as we take enough samples, that eventually the distribution of all the samples looks like a normal distribution. That's, you can see here on these graphs. We start off with n equals 50 and p equals 0.1. So we've got 50 trials, 0.1 is the probability of success at each trial. And you can see that when we do that sampling distribution, that it's kind of looking normal, but it's a bit skewed. It's not exactly right. Once we get up to n equals 100, we increase the value of n. It really does look like a normal distribution now. And the greater the value of n, the more closely it looks like a normal distribution. So the question is, what's the cutoff? How big do we need to be? And what does the value of p need to be so that this looks sufficiently like a normal distribution? Because both n and p come into play. If p is really, really small, so the probability of success is like, 1% at each trial, and you take 50 trials, then you're going to see that the distribution is really skewed towards the lower values down here. So if p is kind of, like more like 0.4 or 0.5, it's much more symmetrical, the distribution that you get when you do all of these samples. Similarly, if you get heaps of trials, like down here, then it looks like a normal distribution, even if p is pretty small. So how do we weigh it up? How do we balance it up? And there's a simple answer to that question. We balance it up so that when n times p is greater than 5, okay? Or n times 1 minus p also has to be greater than 5, because we might have a situation where p is equal to 0.999. So there's a 99.9% chance of something happening. Then of course n times p is going to be greater than or equal to 5, but then n times 1 minus p might be less than 5. So it still might be skewed, but towards the other direction. So we need p to be kind of reasonably in the middle, and we need n to be pretty large, such that these two conditions are met, and then we know that we're going to get a normal distribution, and we can go ahead and use the maths behind all of that stuff. Okay? All right, so let's talk about confidence intervals now. So a confidence interval is a specific interval based around our sample proportion, p with a little hat, and it's within this interval that the true population proportion may lie. So we're going to say something like we're 95% sure, we're 90% sure, or we're 99% sure if we want to do that. So that's what our confidence interval is. And remember, as I've just said, n times p has got to be greater than 5, and n times 1 minus p has got to be greater than or equal to 5. So once we've confirmed that those are true, then the central limit theorem kicks in, we've got a normal distribution, and we can start looking at the probabilities of what's going on. Let me show you a little demo of this confidence interval idea. So here I'm going to take a random sample from a population where n is equal to 100 and p is equal to 0.5. So imagine if we toss a coin 100 times, the probability of getting a head is 0.5, and we do it 100 times and we add up how many heads we get. Okay, so I'm going to do a sample here. Now in this case here, you can see a very unlikely thing happened, that the confidence interval that we generated, and I'm going to show you how to get that in a second, did not contain the population parameter. If I do this many, many times, you can see that the actual sample value, the one right in the middle here, is changing. In this case, we got more heads than tails. Right, so that our p-value, this line here represents p equals 0.5, but the confidence interval that we created contained 0.5. Okay, you can see I do that a number of times. You can see one there was spot on 0.5, That one there was a lot less than 0.5, but the confidence interval still had 0.5 in it. So let me do 10 intervals at a time now. So we did 10 intervals, 9 of them contained 0.5, somewhere in that interval, 1 of them did not. A confidence interval, the way we can interpret it is we could say if we do 100 samples, that 95 of them would contain the true population proportion in this case, and 5 wouldn't. We're 95% sure that the true value lies within our confidence interval. Okay, so for a sample of 10, we're getting 1, sometimes all of them in there. And I could keep on doing all these samples and you can see some of them high, some of them low. Remember, each one of these is us throwing the coin 100 times and counting up how many heads there are and looking at the proportion of heads. So in this one here, it might have been 53 out of 100 heads, or 0.53. We constructed this interval and you can see 0.5 is in that interval. Okay, so a running total now, we've got 91.7. So let's do 100 intervals and do that sample. So we've got 100 intervals now. 1, 2, 3, 4, 5, 6, 7, 8 of them didn't contain the population proportion of 0.5. 8 of them. So we were only expecting 5. So let's do that again. In this case, 1, 2, 3, 4 of them didn't. In this case, only 3. So in the long run, we'd expect that 95% of all of our intervals would contain the true population value. That's the interpretation of a confidence interval. So here's the calculation for it. So what we're saying is the probability that we're looking at z-scores now. So we're looking at our standard normal distribution. And the first thing that you want to know how to do is work out what are the z-scores so that, let's say, 95% of all of the values lie within there. Now this is our standard normal distribution with a mean 0 and a standard deviation of 1. So first of all, let's work out how to work out those z-values. If we go to a calculator now, and I'm going to go to main, and this is going to be an inverse normal problem because I've got the probability and I want to find the z-value. So it's going to be inverse normal CDF. So center is the setting. The probability is going to be 0.95 in the middle. Leave it standard deviation of 1 and a mean of 0. And we're going to go OK. So it gives us the lower value of negative 1.96. Okay, so that is the low value. So obviously the top value is 1.96. So if we're within 1.96 standard deviations of the mean, either way, 95% of all the values will lie within there. So obviously you can repeat this if you want a 90% confidence interval or a 99% confidence interval, and you can get the z-values. It's sometimes good to even memorize these, and back in the old days before you had a calculator, I would definitely memorize these 4 values because they're the most common confidence intervals. We have 90, 95, 98 and 99% confidence intervals, and you can see the z-values for those. You can always work it out on your calculator though. So going back to our most basic formula for the normal distribution, our z-value is x minus the mean over the standard deviation. So in this case here, we will get a z-value, a standard normal distribution, if we take our x value, which is just going to be p hat, subtract off the mean, which we know is p, and divide by the standard deviation. Now we know what the standard deviation is. That is this from the previous video. Okay, so this thing here gives us a standard normal distribution. Okay, and that's important to the start of this little proof. So we know the probability that this z-value here, this thing here, lies within 2 standard deviations of the mean is around about 0.95. So a bit of rearranging here. If we times everything by the standard deviation, we get this step here. So p hat minus p is equal to this. And then a little bit of rearranging now so that we just leave p in the middle. Remember, p is our population value, the thing that we're trying to create this interval for. So going from here to here, it's a little bit tricky, but you could subtract p hat from each of these here, and you get negative p in the middle, swap them around, and you end up with this line here. Okay, so that says the probability, the true population proportion is between that value and this value is around about 0.95. So these two values here are symmetrical and they form the confidence interval based on our sample value p hat. So here's what the confidence interval looks like. It looks really confusing, doesn't it? But really, it's easy because p hat we know. So on my heads example, 53 out of 100 heads, so p hat would be 0.53. So that goes in there, there, and there. N is our sample value. For the one we've just been doing, N was 100. And Z, this thing here, is our level of confidence. So for a 95% confidence interval, that value there is 1.96. Another way you could write it is just like this, p hat plus or minus this thing here, because it's a symmetrical confidence interval. So the way that it appears on your formula sheet is exactly like that. Okay, so what are the factors that influence the width of the confidence interval? You can see obviously it's going to be n. The bigger the value of n, the smaller your confidence interval is going to be, because n's down there. So if we increase the value of n there, you can see this whole thing is going to get smaller. So the width of the interval is going to get smaller. The other thing is this z value here. The bigger this z value here, the wider your interval. So if you want to be 99.99% confident, then this z value here is going to be big and your interval is going to be really wide. So that's why we choose, 95% as being pretty reasonable statistically. If you go for a really high, you can say I'm 99.99% confident that my population proportion lies between 0.1 and 0.9. I mean, that's boring, isn't it? You could say, yeah, you're really confident, but the interval is so wide that it's meaningless. We need to zone in a little bit here. So they're the factors that influence the width of the confidence interval. The z value, or the level of confidence, and the n, which is our number of trials. Okay, finally, let's do one of these. A sample of 500 people are surveyed has found that 60 of them are left-handed. Calculate a 90% confidence interval to estimate the proportion of left-handed people in the population. All right, let's write it all down. So we've got p hat is equal to 60 out of 500. Okay, I'm going to get my calculator going here. 60 out of 500, which is 0.12. So 12% of the people in our survey were left-handers. Now we're trying to estimate the proportion of all left-handed people in the population. How good was our sample? Again, we've got to do our sampling right. So this is a random sample and all of that sort of thing. We didn't just ask the first 500 people that we saw down the shops that it was random, all of that sort of thing. Okay, so p hat is 0.12. What else do we need to know for the formula? We need to know n, which is 500, and we need to know z, which is our level of confidence. So our level of confidence for a 90% confidence interval, you can check it on your calculator, is 1.645. And then we just put it all in the formula. So our confidence interval is, let's say a 90% confidence interval is going to be p hat plus or minus z, this thing here, which is, so it's what's called the standard error, but it's the standard deviation of the sampling distribution. Okay, so 0.12 plus or minus 1.645, 0.12 times 1 minus 0.12 over 500. I always put this step in here where you actually work out that thing on the end. So 0.12 times 1 minus 0.12, just do this one step at a time, gives us that. Divide by 500, gives me this. Square root that answer, gives me this. You could do this quicker way on your calculator if you like. Times 1.645 gives me that. So it's 0.0239. So that is 0.12 minus that answer is going to give me the lower end, 0.096. And we normally use these square brackets for confidence intervals. And for the upper limit, 0.12 plus 0.0239 gives us 0.1439. We'll just go 3 decimal places for today. So 0.144. There's our 90% confidence interval. So I'm going to interpret that to mean that 90% of the time, if we did 100 confidence intervals, we did this 100 times, 90 of our confidence intervals would contain the true population proportion on average. Or we could say for these actual numbers, we're 90% confident that the true population proportion lies in this interval somewhere, which is between 9.6% and 14.4% of people in the population that are left-handed. So these are important. Is it 9.6%? Is it 14.4%? At least we've got a gauge or a range that we've narrowed it down with 90% confidence.